A doctor tells you a test is 99% accurate. You test positive. Most people hear that and think there is a 99% chance they are sick. They are almost certainly wrong. And explaining why requires starting from the very beginning. A single coin, landing on a table. Probability begins with counting. One coin. Two sides. Flip it, and the chance of heads is 1 in 2. That is not a deep philosophical statement. It is an act of counting, one favorable outcome divided by two possible outcomes. Two coins. Each can land heads or tails, independently. That gives 4 equally likely combinations. Heads heads, heads tails, tails heads, tails tails. The chance of both heads is 1 in 4. 3 coins give 8 combinations. 4 coins give 16. Every coin you add doubles the number of possible outcomes. By 10 coins, you have 1024 possible sequences. By 20, over 1,000,000. The combinatorial explosion is the first thing that makes probability hard to think about. We can hold a coin in our heads. We cannot hold 1,000,000 sequences. But the maths does not care about what we can hold. It just counts. 2 rules govern almost everything in basic probability. The addition rule and the multiplication rule. If events are mutually exclusive, the probability of either one happening is the sum of their individual probabilities. Roll a die. The chance of a 1 or a 2 is 1/6 plus 1/6, which is 2/6 or 1/3. If events are independent, the probability of both happening is the product of their individual probabilities. Flip a coin and roll a die. The chance of heads and a 6 is 1/2 times 1/6, which is 1/12. These 2 rules are extraordinarily simple. And yet they are sufficient to derive nearly every result in introductory probability. Addition for or. Multiplication for and. That is essentially the entire grammar. When you apply these rules to repeated experiments, patterns appear. Flip a coin 10 times and count the heads. You could get 0 heads. You could get 10. But some totals are far more likely than others. Getting exactly 5 heads has 252 different sequences that produce it. Getting 0 heads has exactly 1 sequence, all tails. Plot the number of ways to get each total, and a bell shape emerges. This is the binomial distribution. It is not an assumption. It is not a model imposed on reality. It is what counting produces when you let it run. The bell shape is not a choice. It is a consequence. From distributions, we extract summaries. Expected value is the weighted average of all possible outcomes. For a fair die, the expected value is 3.5. You can never actually roll a 3.5, but it is the number around which reality clusters. Think of it as the balance point of the distribution. If you rolled a die 1,000 times and averaged the results, you would land very close to 3.5. Variance measures the spread. A die has moderate variance. A coin labeled 1 in 1,000,000 has enormous variance. Same expected value as rolling a die scaled up, but the experience of living inside that distribution is completely different. Expected value tells you where. Variance tells you how wild the ride is. Now we reach the idea that breaks most people's intuition. Conditional probability. The probability of A given B is not, in general, the same as the probability of B given A. This sounds obvious when stated abstractly, but humans get it wrong constantly. Consider, the probability that a person has 4 legs, given that they are a dog, is very high. But the probability that something is a dog, given that it has 4 legs, is not. Tables, cats, horses, and elephants all have 4 legs. Swapping the direction of a conditional changes the answer completely. And yet in courtrooms, hospitals, and newsrooms, people swap them every single day without noticing they have made an error. The prosecutor says, The chance of this DNA evidence appearing if the defendant is innocent is 1 in a million. The jury hears, the chance the defendant is innocent is 1 in a million. Those are not the same statement. And the gap between them has sent innocent people to prison. This is where Thomas Bayes enters the story. A Presbyterian minister in 18th century England, Bayes asked a deceptively simple question. If I know the probability of B given A, and I know the overall probability of A and B separately, can I calculate the probability of A given B? The answer is yes, and the formula is Bayes' theorem. P of A given B equals P of B given A, times P of A, divided by P of B. That is it. One formula. It tells you how to update your beliefs when you receive new evidence. It tells you how to reverse the direction of a conditional. And it explains why the doctor's test at the beginning of this video is not what you think. Let us go back to that medical test. 99% accurate. You test positive. Here is the information you need. Suppose the disease affects 1 in every 1,000 people. The test correctly identifies 99% of people who have the disease. It also correctly identifies 99% of people who do not have the disease. In other words, it has a 1% false positive rate. Now imagine testing 100,000 people. 100 of them actually have the disease. The test catches 99 of those. But of the 99,900 healthy people, 1% test positive by mistake. That is 999 false positives. So when you test positive, you are one of 99 plus 999 positive results. 99 real cases, 999 false alarms. The probability you are actually sick is 99 divided by 1098. That is about 9%. Not 99%. 9%. The test is accurate. Your conclusion was not. What went wrong is called base rate neglect. Humans instinctively focus on the test's accuracy and ignore how rare the condition is. When the disease is rare, even a very accurate test produces more false positives than true ones. The base rate, 1 in 1,000, dominates the calculation. But our brains do not naturally weight base rates properly. We hear 99% accurate and our intuition just writes down 99%. This is not stupidity. It is a systematic flaw in how human cognition handles probability. Doctors make this error. Judges make this error. Entire national screening programs have been redesigned because of this error. The maths is not hard. The formula has 4 terms. The hard part is remembering to use it instead of trusting your gut. Which brings us to the ultimate test of probabilistic intuition. The Monty Hall problem. You are on a game show. 3 doors. Behind one door is a car. Behind the other 2, goats. You pick a door. Say door 1. The host, who knows what is behind each door, opens another door to reveal a goat. Say door 3. Then the host asks, do you want to switch to door 2? Most people say it does not matter. 50-50, they say. 2 doors left, 1 car. They are wrong. Switching wins 2/3 of the time. Staying wins 1/3. When this problem was published in 1990, nearly 1,000 people with doctoral degrees wrote angry letters insisting the answer was 50-50. Paul Erdos, one of the greatest mathematicians of the 20th century, refused to believe it until someone showed him a computer simulation. Here is why switching works. When you first picked, you had a 1 in 3 chance of being right. That means there was a 2 in 3 chance the car was behind one of the other 2 doors. The host then removes 1 wrong door from that group. But the 2/3 probability does not disappear. It concentrates onto the 1 remaining door. Think of it this way. If there were 100 doors and you picked one, then the host opened 98 doors to reveal goats, leaving only your door and 1 other. Would you switch? Of course you would. The host just told you, in the most dramatic way possible, which door has the car? The three-door version is the same logic, just less obviously dramatic. The host's action gives you information. Switching uses that information. Staying ignores it. And ignoring free information is almost never optimal. Probability starts with the simplest possible question. You flip a coin. What can happen? And from that one question, following the logic wherever it leads, you end up with Bayes' theorem, conditional reasoning, and results that contradict every instinct evolution gave you. The coin does not lie. The die does not lie. The maths never lied. But your brain will, confidently and repeatedly, because it was built for a world of saber-toothed tigers and seasonal fruit, not for a world of false positive rates and conditional probabilities. Probability is not about luck. It is the study of what happens when you count carefully and refuse to let intuition fill in the blanks. One coin. Two sides. And everything else follows.